Okay, hello everyone and welcome to another session of Programming Languages Semantics. Uh, I guess I have to say Happy Chinese New Year because there's so few of you here. And let's just make sure that we record this so that people who cannot attend can later watch it. Yeah, and I should also apologize for the previous session. I forgot to record that session, so yeah, that one's going to be missing for now. Okay. Today we're just going to see a completely different flavor of semantics. Uh, Basically, I'm going to cover axiomatic semantics, and the coverage is going to be very similar to the previous cases. We write the rules together, we talk about how they work. And this is actually the last session that would be focused on semantics. And from next week on, we will just switch to algorithmic aspects of verification. So the next session is going to be focused on two-player games on graphs, which is suddenly quite a shift. So we go out of this 4-1 semantic world and go into a more graphical kind of world. And then we will continue with that. And towards the end of the course, all of the topics will converge and you will see how everything just fits into each other. But for now, I'm just going to talk mostly about axiomatic semantics. So let me share my screen. And in the chat box as well. So we've already seen two different types of semantics, two different paradigms for defining semantics. The first one was operational semantics, which basically thought of programs, the meaning of programs as how they execute. So the idea there was that we defined transitions and we said, okay, the program transitions according to specific rules. And these rules are the meaning of the program. So that was operational semantics. Then we saw a completely different viewpoint, the viewpoint of denotational semantics, where it said that programs are basically just functions that change the valuations. There are functions that map initial values or inputs to final values or outputs. And we saw how that worked. And today we're going to see a completely different approach, and the approach is actually that of axiomatic semantics. This is the kind of approach that was initially introduced by Hoare. So what we see in this session is also called Hoare's logic or Hoare logic. And so the idea here is quite different. Instead of focusing and nitpicking about the actual execution of the programs or what the exact output or input is, what we're going to do in this session is basically trying to figure out how we can reason about programs. And let me just show you a motivation for this. Consider this program here. And please read it with some accuracy. And can you guess what this does? It's a very simple program. So what do you think this program does? You can either talk to me or write in the chat box. Right. It basically sums up all of the powers of 2 from 2 to the power of 0 to 2 to the power of n minus 1 and puts them in S. So it basically computes 2 to the power of n minus 1, right? And let's say that we want to prove that this program works correctly. What do I mean by that? I mean that I want to prove that at the end of this program, we will always have S equal to 2 to the power of n minus 1. Okay. Or maybe we want to just prove that it's less than 2 to the power of n. So how would you go on trying to prove this? So you've already seen two types of semantics. Which kind of semantics is better for trying to prove this, and how can we do that?
Maybe we can show the number of increase of S in each loop iteration and then accumulate these effects to get the final answer.
Yes, that's correct. But which kind of semantics do you want to use? Can you do it using one of the two different types of semantics that we've seen?
I'm not sure whether denotational semantics can prove this.
Okay, so the problem with denotational semantics is that actually computing it is quite hard. So what we did with denotational semantics was that we basically assigned a meaning to this program, which was a function from the initial state to the final state. Now, computing that function is not such an easy task, right? So you can't just compute, especially because the part that handles the while loop goes into fixed point theory, and then computing fixed points is not easy. So if you want to prove this correctness in an automated way, you have very little chance with denotational semantics because, well, basically you can't compute the function itself, and without that, you don't really have denotational semantics. Uh, what about operational semantics? Can you somehow use the operational semantics of this program to prove that at the end this thing holds? Actually, this is possible, but it's a bit hard. And the way we can do it is similar to how I think it was in the second session. We wrote a proof for termination of a given algorithm. And we wrote that proof with basically induction and uh, using the big step operational semantics. Yes, and here what we can do is basically very similar. We can do an induction, and we can basically do induction on n, and then follow the operational semantics. But you see, the problem with this approach is that it's not really easy to automate it, because in this case we have so many different variables. For example, we have n, I, s, m, and in real world cases we will probably have even more. And it's not really obvious what we have to do the induction on. Like, do you do induction on n? If that's the case, why aren't you doing induction on s? And how does an automated algorithm figure that out? That's quite hard, actually. And the previous case, which was about termination, if you remember, we had this value which we defined, which was basically the value of x in a valuation plus the value of y in the same valuation. And then we did induction on this combination in our previous proof. Now, this is again something that is really non-trivial. If an automated verifier wants to prove that this program is correct, it can't really just magically figure out that it has to do induction on such a combination of variables. And why this combination? Why not some other combination? So this is not very useful. A human can probably create a proof for correctness of this program based on operational semantics, but then it can't be automated. So what can we do to actually automate it? So let's just think of the initial way that was suggested for proving that this program is correct. And the initial way was to rely on neither operational semantics nor denotational semantics and just talk about what this program does, right? In a sense, this is like adding extra information into the program. So whenever I want to add extra information, I write it between curly braces. So at the beginning of the program, we know that n is greater than 0. We can assume this. It wasn't really in the program, but let's just assume it. And then when we run one step of the program, well, this step didn't really change n, so we already know that n is greater than 0, but additionally, we also know that I is equal to 1. So at this point of the program, our knowledge is a little bit more than the initial. And then we run another step, our knowledge increases again. And now the question is, what do we know at this point? And I've already written the answer, but can you give me some intuition about why I'm writing this? Why am I not just writing that n is greater than 0, I is 1, s is 0, and m is 0? Why is this one suddenly different? Any ideas? Yes, because this is before this loop. And so when I talk about this point of the program, the only way to reach it is not from the beginning of the program. There are also other ways of reaching this point. And the other ways are to go through this while and come back. And that would also reach this point. And what we're doing is that we are basically writing assertions that are correct at this point of the program whenever the program reaches here. Right. So I know that the program reaches this point only once, and when it reaches here, this assertion holds. But because the program might reach this point many times, then I have to make sure that the assertion that I'm writing here actually holds in all of them. And then, of course, we can write more inside the while loop if we want to. And at the very end, we have this other assertion. Now, these assertions that basically any assertion that always holds when the program reaches the point is called an invariant. So this is an invariant because we know that in every execution of the program, when we reach this point, this assertion holds. And you can also verify that the rest of it are also invariants. So this is an invariant, this is an invariant, and so on. Now, we will actually see some approaches for generating invariants towards the end of this course if we have time. But for now, let's just see how we can verify an invariant and how the invariants help us in actually proving that this program is correct. You see, I can actually do some sort of induction with the invariants. What I can do is I can say this: if my initial assertion holds, this one, which we assume holds in this case, and if in every step of the program I never falsify the invariant, then I can be sure that the invariant always holds, right? So I start here, I know that n is greater than 0. And the step that I can have here is to basically execute I equal to 1. And then this doesn't falsify my next assertion. So this assertion will stand. And then again, I can do the same thing from this assertion to this assertion, and also from here to here. So if I'm at this point of the program and I know that n is greater than 0, I is 1, and s is 0, and then I apply this assignment, apply m equal to 0, then I'm sure that this whole thing holds, right? Why? Because, well, n was already greater than 0, m is 0, so it is greater than or equal to 0. N is greater than or equal to m, it holds because n was greater than 0 and m is 0. And you can also check this by simple calculation that it holds. So the step that I have from here to here does not falsify my assertions. Okay, what else can I have? So when I'm here, I can actually have one iteration of the loop. And I start with this assertion. I do one iteration of the loop, and I come back. And I want to see if the same assertion holds. So if this assertion initially holds, again, you can just do a calculation and see that these things work and they will all hold. But there are two cases actually. So one case is when you go inside the while and do a loop and do an iteration and come back. And the other case is if the while condition does not hold. And if the while condition does not hold, then I will basically just step from here all the way to here. So I have to prove that in that case, this assertion will hold, assuming that this assertion held at the beginning. Okay, that's also easy. So if this assertion initially held, then I know that S was this thing, which is basically 2 to the power of m minus 1, right? And also we didn't go through the while loop. So this means that the condition of the while loop was false. So this means that m was greater than or equal to n. But on the other hand, I have the assumption that n is greater than or equal to m. So from these two things, I know that whenever I transition from here to here, m and n have to be equal. And because they are equal and because s was 2 to the power of m minus 1, then of course s is 2 to the power of n minus 1. So as you see, this is also some sort of inductive proof. Basically, we assign different assertions to different parts of the program, and we just show that the assertions hold at the beginning of the program and that every step of the program or every iteration of the while loop keeps these assertions. And then if at the end I have the assertion that I like, then I have proven that the program is correct. So this is the theme of what we're going to see mostly today. But the idea is, how can we write formal rules for this? And how can we actually formalize it in a way that a machine can, well, hopefully find these proofs? But even if it cannot find these proofs, how can we make them formal enough that a machine can at least check the proofs? So if I give this to my verification system, I want it to be able to check and say, okay, this is actually a correct proof. Okay, so before going on, so I defined what an invariant is. An invariant is basically an assertion at a point of program that always holds when we reach that point. But there are two special cases. So one case is if the assertion is at the beginning of the program, we usually call it a precondition. And then if an invariant is at the end of the program, we usually just call it a postcondition. And we're also going to see different definitions for precondition and postcondition throughout this course. Okay. So let's actually get to the important part of the work today. And let's start by defining a Hoare triple. And a Hoare triple is basically, well, a triple which consists of three different parts. So it's of the form A, P, B. And in this triple, P is a program. So this is our program. Just write it. Okay. And A and B are just some assertions. They are basically Boolean expressions, or maybe assertions in any other language that you like. So you can have assertions in any logical language. Like this one is also an assertion. And when I write something like this, when I write this triple, this big triple, what I mean by this is the following logical sentence. Basically, what I mean is that A is a precondition and B is a postcondition. So what this says is that if you have a valuation that satisfies A and you run your program P and it terminates, the valuation that you get at the end of it will satisfy B. Okay, so let's say this again. So this is what I'm assuming to hold at the beginning of my program, some assertion that I assume holds at the beginning. This is the program itself. And this is some assertion that I want to hold at the end of the program. And when I write this triple, what I mean is that if this initial assertion holds at the beginning, and I run my program, and if it terminates, then the state in which it terminates will satisfy my final assertion. And so I would use this notation throughout the course, but in some courses and books, you will also see this notation. So they are exactly the same thing. Don't worry about it. You can put brackets around the program or around the assertions. And if we want to say the meaning of this sentence in terms of our operational semantics, we can basically say that if I have an initial value and that initial value satisfies A, and if when I execute P from that initial value, I end up at some other value val prime, then this other value should satisfy my post condition B. Okay? So that's the meaning of four triples. But one thing that you should really be careful about is the exact definition here. So what we are saying is that B will hold only if P terminates. So here, assuming that P terminates starting from val, we require that the final value actually satisfies B. And if P doesn't terminate starting from a given valuation, then this triple doesn't say anything about it. Okay, so let's do some examples. I want you to tell me why each one of these four triples actually holds. So the first one is easy. And the first one, we are assuming true at the beginning, which means that our precondition is basically nothing. We are not assuming anything. And the program that we run just assigns 12 to X. And as a post condition, we know that after this program ends, of course, X would be 12. So this is easy. So why does the second one hold? This one is also easy because, well, y was greater than 10 and you put the value of y into x. So the value of y has not changed, so it still remains greater than 10, and x is also now greater than 10. Similarly, this one is easy. If x is greater than 0 and I increase it by 10, of course, it's greater than -2. This one, oh, this one has a typo. I'm not sure what I wanted to write there, but this one is definitely false. So for example, if a is 2 and you do x equals to a times a, then the absolute value of x would not be equal to x, so this one's false. Okay. Now, can you do the hard one? Can you tell me what this triple says and why it's correct? So any ideas why? Let's just first see what the triple says. What does this mean? So we have two variables, x and y. And initially in the precondition, all we are assuming is that they are greater than or equal to 1. And of course, we are also assuming that they are integers because our programming language was specified over integer variables only. And so what's happening in here is the Euclidean algorithm for computing the greatest common divisor. And then at the end of it, if it terminates, we want the GCD to be computed, right? So we want the GCD of x and y to be maximum of x prime and y prime. So this is actually important. So even if you prove this triple, it doesn't prove that this program is totally correct. It only proves that the program is partially correct. It proves that if this program terminates, then the GCD is computed like so. But if this program doesn't terminate, then this says nothing about the program. Okay. Now, these last four ones are things that I really want you to contribute and say why you think they're correct or incorrect. Okay, consider this one. Let's just do a poll in the chat. Please say if you think it's correct or incorrect. If you already have one correct. Does anyone think this rule is incorrect? I'm sorry, this triple is incorrect. Okay, no, so everyone agrees that it's correct. Why is it correct? Right. So at the beginning, you have basically an assumption that is wrong. Like this is unsatisfiable. X times x can never be greater than less than 0. So it doesn't matter what you write following this, because if you go back here to the definition, there is no valuation that satisfies the precondition. So this side is definitely false. And when this side is false, the whole thing is always true. Okay. How about the second one? This one. Is this correct or incorrect? Again, write in the chat. Do you think this is correct or incorrect? Okay. Again, we have another correct. Does anyone think it's incorrect? Okay. So why is it correct? Yes, exactly, because of non-termination. So you have this while loop here that doesn't terminate at all. And again, if you go back to the definition, if it doesn't terminate, you will not have this part. So again, the whole thing holds. Okay, the third one. This one is also correct, again, because of non-termination. So basically, if your program doesn't terminate, the triple tells you nothing. And the last one is also still correct because the precondition is again unsatisfiable. So these were some examples of Hoare triples, just so that I make sure you have the right intuition about them. Okay. And now let's go to the meat and the most important parts of Hoare's logic. So basically, we know what triples are now, but what is it that we want to do? We want to prove that programs are correct. And what that usually means is that we have some precondition and some post-condition, and we want to show that they hold. So we want to be able to prove Hoare triples. Right now, what we did here was that we just intuitively said that these Hoare triples are correct. But we have to have a way of formalizing and mechanizing the proofs. And this is what we do here now with Hoare's logic. And of course, it's going to be rules again. And of course, the simplest rule is always the rule for skip, and we call this the skip axiom. So basically, if your program is just skip, and if your precondition is some condition A, then you can use the same A as postcondition. And this, so when I write a rule like this, it means that this whole triple holds no matter what. So we don't really need any assumptions, and this whole thing holds. Okay. Now, what can we do for assignment? So before actually seeing the rule, let's try some examples. So let's say that my program is just assigning y to x, and my post condition is x is less than n. What should my precondition be? With what kind of precondition can I prove this? Just give me some precondition that you think I should put here. Right, yes. If I know at this point at the beginning of my program that y is less than n, and then I run this program, of course the program always terminates, and I will have x less than n. Okay, how about this one? So everything is like before, x is less than n as the post condition. And the only difference is that I'm just increasing the value of x by 2. So what should I write as the precondition here? Okay, so one suggestion is to write x is less than n minus 2. That's almost correct, but not exactly. What we want here is x plus 2 is less than n, yes. And these two things might seem like they are the same thing, but actually they aren't, in the sense that if you have a program that basically just checks the rules, then it does it very formally. And by formally, well, it's in the name. It means that the form actually matters. So this is different from x is less than n minus 2, even though they are equivalent. Okay, so based on this, we can have the following rule for the assignments. So whenever I do an assignment and assign, let's say, some expression e to x, if I want a to hold at the end, then in the beginning I should have the same a holding, except that here I should put the value of e in x, right? And this might be a little bit counterintuitive, but if you look at this example, you figure it out. So basically, the new value of x becomes this x plus 2. So if I want the new value of x to be less than n, then I need the value of this expression to be less than n before. And this is the same thing here. So the new value of x is the meaning of e, the valuation of e. So if I want a to hold at the end, I should probably have this thing, basically a with x replaced by e to hold at the beginning. And so you would have noticed that I talked about the skip axiom, but about assignment axiom schema. So the thing is that this is a single axiom because skip is a single program, right? But this is actually not a single axiom, not a single rule. It's a family of rules based on all the assignments that we can have. Okay, so let's continue with this. Now, what can I do for sequential composition? Again, let's start with an example. So let's say that my program simply increases x by 1. And at the beginning, I had the assumption and the precondition that x is greater than 0. So of course, at the end, I can have x greater than 1. And the same thing goes for this one. Now, if we have these two assumptions, if we just assume these two Hoare triples, we can actually just put them together and deduce the Hoare triple in the bottom. And what's happening here is that, well, I'm starting with the precondition that x is greater than 0. And I'm running x equals to x plus 1. So at this point here, I will have x greater than 1, right? And then with this precondition, based on this second triple, I can run x equals x plus 2. and then I will have the post condition. So that's actually quite intuitive. So how do we write this in the general form? Can you write the rule in the general form? So I can actually write the bottom part first. So if I have a program that is a sequential composition of P and Q, and I want to have this Hort triple, which basically says that the precondition is A, the program is P semicolon Q, and the post condition is B. Okay. So what should I put as the assumptions of this rule? What should I put above the line? Yes, that's correct. So if I have A, something like this, and so basically it's the same principle as before. So I first run, I start knowing that A holds. I first run P. Either it doesn't terminate or it terminates in a state where C holds. And then I run Q, which leads to which again either doesn't terminate or leads to a state in which B holds. So I can have this rule for sequential composition. Okay, let's now make it a bit harder. What rule should we write for if? So now what I want is that I want my program to be of this form. When will I have this? So in operational semantics, what we did was that we just wrote two different rules for the different cases, right? But here we can't really do that. Because when we are talking about a Hort triple, it's basically talking about all executions of the program in here, right? It basically says that every execution that starts from a state that in which A holds and terminates should terminate in a state where B holds. So this sentence is not talking about a single execution of the program, it's talking about all executions. So we need to somehow capture this object. Yes, that's actually correct. But you don't need the semantics there. You can just put A and B, right? So in order for this to hold, we again take two cases. So the first case is if the if condition holds, then that would be similar to just running P. So that's the first assumption that we need. And the second assumption that we need is if it doesn't hold, so then this happens, right? So if we have these two assumptions, then both cases are covered, and we know that this Hort triple also holds. Okay, yes, and the things in the chat are correct. So before going on, let's see if we can actually prove something using the things that we already have. So let's say that I want to prove this Hort triple. So I want to prove that if my precondition is that n is greater than 1 and then I run this program, then I will have x greater than 0. And the program basically says that if x is less than n, then assign n to x. Otherwise, just increase x by 1. So you all agree that this is a correct or valid Hoare triple, right? But how would we prove this? So now I'm trying to write a formal proof using the rules. What rule should I use here? I have only one choice for the rule that I have to use here, right? Because this is an if, the only choice that I have is to just apply the if rule. And the if rule has this format, so I can just write these things down. And these are the things. So basically, if the precondition holds and the if condition also holds as the precondition, as the whole precondition here, and then we just have to do what the then part does and get the same post condition. And this case is also similar. If the precondition holds, but the if condition does not hold, then we have to do the else part and get the same post condition as before. Okay. But how would we prove these things? So let's say that I want to prove this one first. I want to prove this triple, which basically says that for any starting valuation that satisfies n greater than 1 and x greater than or equal to n, if I run this program, of course it always terminates, I will reach a final state in which x is greater than 0. Now, well, this program here is an assignment, so I should somehow run the assignment rule. But if I write the assignment rule for this, and the assignment axiom for this specific assignment, this is what I get, right? So if I want my post condition to be x greater than 0, which I want it to be, then according to the assignment rule scheme, basically assignment axiom scheme, I have to have x plus 1 greater than 0 as my precondition. But now, as you see, there is a gap here. Somehow we have to get from this expression to this expression. Right? And so naturally, when as humans we are thinking about this, this makes sense, right? Because what am I doing here? So the program and the post condition are the same. And here what I have proven is that it's enough if in the precondition I just know that x plus 1 is greater than 0. But what I know here is actually much stronger, right? I know something about n. I know that n is greater than 1. But I also know that x is greater than or equal to n, which in turn gives me x plus 1 greater than 0, of course. So logically, this makes sense. If this one, if the upper rule, if the upper triple holds, then this one should also hold. But the problem is that we actually need a rule for this. We need to have a rule so that a machine can again check the proof. So I need to be able to just put a bar here and say that from this I can get to this. But I don't have it right now. So let's see what happens on the other side. On the other side, again, I have an assignment and I know the post condition. So according to the rules for assignments, I know what kind of precondition I can have. So this is what I can know about this assignment. And here again, we have, oh, okay. So I also changed the post condition. And if I know that n is greater than 1 and I do x equals to n, I would know that x is also greater than 1. But now here again, I have two problems. So the first problem is that the post conditions are not the same. And the second problem is that the preconditions are not the same. Now, in terms of preconditions, this doesn't really matter for the same reason as before, because this precondition is actually stronger than this one, right? So that's okay. And then this post condition is weaker than this one. So this should also be okay. So logically, it makes sense that if you prove this triple, then you should also have this triple. But again, we need a rule that says this. So let's go on and just try to define these rules. And these are what we call the rules of consequence. So the first one is exactly what we used in the previous slide. You can basically strengthen the precondition. So if you know that this triple holds, so with the precondition A, you know that when you run P, you will get the post condition B, right? Now, if you make your precondition stronger, if you choose some A prime such that A is always a consequence of A prime always implies A, then this, of course, is fine because, well, A prime, you can basically have this triple because, well, A prime gives you A, and then you already know that if you had A and ran B, you would have, and ran P, you would have B. So this triple also holds. And this is actually just the intuition. We accept this as an axiom, actual axiom schema. And similarly, we can, of course, weaken the post condition. So if starting from A and running the program P, I end up in states that satisfy B, assuming that P terminates. And if B then implies some other B prime, then of course, in all of my terminating states, B prime also holds. So I can have the triple A, P, B prime. And actually, the way that Hoare originally did it is to just put all of these together and just say that you can strengthen the precondition and weaken the post condition as much as you like. And you can do it at the same time. So is this clear? And the idea is very simple. Okay, so now we can actually go on and do our example. And we can explicitly say which rules we are applying. So here, the rule that I'm applying is the rule for if. And the rules that I'm applying here are basically the rules of consequence for the precondition and postcondition. And well, these are just the axioms that we had for assignment, right? So this is just assignment. Or maybe I can just now, here's where you can actually see the main difference between this kind of semantics, which we call axiomatic semantics, and what we had before in operational semantics. So operational semantics was also rule-based, but all of these sentences that we had in our rules talked about only one transition in the program or only one execution of the program if it were a big step. But in this case, as you see, we are talking about all of the executions from, well, not exactly all of the executions, but all of the executions from a given precondition. So this is much more powerful. And as you see, this is a complete proof for this Hoare triple, and it didn't use anything other than our rules. So I didn't have to define something on the side and do some sort of induction on it. I could just follow the rules. Okay. And of course, like all the previous cases, the main question is what happens with while? the while rule is always the most complicated rule. Okay, again, let's just do an example. So let's say that my program is this. Basically, while x is at most 100, I increase x by y, and I know that y is greater than 0. So what can I put as the post condition here? And of course, I can put true as the post condition. So I don't want that. Just give me something interesting as the post condition. Right? We can have x greater than or equal to 100. And why? Because, well, if this while has ended, then what do we know? We know that the while condition did not hold in the last iteration, and that was why it terminated. So yes, of course, we know that x is greater than or equal to 100. What else do we know here? Yes, we know that, well, the fact that we know that x is greater than or equal to 100 is also covers that x is greater than or equal to 90 and so on. Yes, we also know that y is greater than 0 because, well, we assumed it in the precondition, and of course we didn't touch y, so it holds in the post condition. So this is the while rule that we usually use, but just one small detour here. In this specific case, we also know something else. So you said that we know that x is greater than or equal to 100. So that's what? That's a lower bound on x. Can you also give me an upper bound on x? Yes, x is at most 100 plus y. But I'm not going to actually add this here because this is something that is very specific to this while loop. So the other things were things that you can do in general. So if you have a precondition and you don't touch it during your while loop, you always know that you can have it in the post condition. And oh, right. Okay, what if we have a large initial x? That's right. So in that case, we will not have any. Yes, in that case, we will not have any upper bound on x. So maybe what I meant was to say that x is also small at the beginning. So let's say I know that x was less than or equal to 0. So if I had also that, then I could say that, okay, x is also bounded by 100 plus y. Yes. Good point. I wasn't paying attention to that point. Right. But let's not talk about this. Let's just talk about this. So the idea here was basically two different things. The first idea was that if you have a precondition that is not touched by the while loop, that basically holds all along, then you can just use the same precondition in your post condition. And also, when the while loop terminates, you know that its condition, the guard of the while, does not hold anymore. So let's just use these two things to write a while loop. So here I have A. So let's say I have some precondition A. And following the idea before, what I want to do is that in here, I want to know that B does not hold, of course. And I also want to still have A somehow. But what are the assumptions that I need for this to hold? So basically the assumption should somehow match our idea here that this while loop does not really change this initial assertion and doesn't falsify it. Yes, exactly. So it's A, P, A. So if running P from A does not falsify A, then we would be sure that this holds. But actually, this is too strong. We can make it a little bit weaker. Yes. We can basically say this. Because we only run uh, this part P if B holds, right? And if B does not hold, then we don't really run it. We just go from here to here. And okay. So this is the while rule. Basically, it's a bit different from the previous rules in that we are just working with some precondition A, and this A just keeps staying with us, right? So this is what we call a loop invariant. So A is a loop invariant in the sense that it never gets falsified by an iteration of this loop. And this is our while rule. Okay. So do you think we need any other rules? Or do you think these rules are enough? Actually, I'm going to let you think about this, and I'm just going to tell you about the homework, and then we'll come back to this. So the homework that I'm assigning this time, and I want you to do this by 25th, which is like 2 weeks from now, is this. So this is our favorite program, the one that computes greatest common divisor, and we've seen so many times. And I want you to actually write a formal proof that this program is correct. So I want you to write a formal proof for this whole triple. So the triple is, this is the precondition, x greater than 0 and y greater than 0. This whole thing is the program. And then this is the post condition that I want you to prove. That basically we get the greatest common divisor of x and y into this variable z. And just to make the homework more precise, I also give you the definition of GCD, greatest common divisor. So we say that some number d, and we always want this to be greater than 0, is the greatest common divisor of a and b. Well, of course, if it's a divisor of both of them, so it should divide both a and b. And also, if there is another common divisor, for example, d prime, that divides both a and b, then we want d to divide d prime. So this is the definition of GCD. So what I want you to actually prove is this as the post condition. And give me a formal proof of this. And please don't use the operational semantics because it's also doable with operational semantics, but try to do it only with Hoare triples and the rules that we saw in this session. Okay, and a second thing that I want you to do is to read this paper. This is a very classical paper by Tony Hoare, where he basically defined all of the things that we saw in this session. It's called An Axiomatic Basis for Computer Programming. And okay, no, this wasn't the point that I wanted to talk about. This one. Okay. Let's not go there. Let's just ask the same question again. So we saw all these rules. We saw the rule for if, for while. We saw the rules of composition. We saw the rules of consequence, which were actually new here. We didn't have anything similar to the rules of consequence in the previous kinds of semantics. But what I want to really ask you is, do you think these rules are enough? Or are there cases where we would need more than these rules? So specifically, I'm talking about a rule like this. Well, first of all, can you tell if this rule is correct or not? So intuitively, why does this rule hold? Well, the first triple up here is saying that if I start with a valuation that satisfies A and I run P after and the thing terminates, then I'm in a valuation that satisfies B. This is similar, but it only says that the final valuation satisfies C. And of course, if the final valuation satisfies B and satisfies C, then it will satisfy B and C. So the rule is correct. But do we need such a rule? So does this rule change the set of Hoare triples that we can prove? Is there anything that we can prove using this rule that we cannot prove only using the previous rules? Okay, let's do another poll. Who thinks this rule is needed? So just write yes or no. Write yes if you think we need such a rule, and write no if you think we don't need it. Okay, we have one no. Anyone who thinks we need it? Okay, we have two no's now. So why don't we need it? Can we somehow get this as a theorem from the other ones? No, you can't get it from the consequence rule. Because let's go back to the consequence rule and see. Okay, so the consequence rule basically says that you can weaken the post condition. So in this case, we are not really weakening the post condition. In this case, the post condition that we have, this is B and C, which is stronger than just B, and it's also stronger than just C. So we are not weakening, we are just merging them together. So another answer is that this one holds by the definition of Hoare triple. Yes, but all of the other rules also hold by the definition of the Hoare triple. So we are doing two different things. On the one hand, we are giving a definition for what a Hoare triple means, which was at the beginning of this lecture. And on the other hand, we are giving some rules for finding Hoare triples, right? And using these rules, we can write proofs for Hoare triples. And all of our rules are correct in the sense that if we have a proof for a Hoare triple, then that triple holds. But the question is, do we need this rule in the sense that can we prove something more with this rule that we could not prove with the previous rules? Of course, you can prove everything with the definition, but this question is with regards to the previous rules. So is there, for example, a Hoare triple that you can prove and use this rule in the proof, but you cannot prove it if you don't have this rule and only have the previous rules? That's my question. different proof could go to either B or C. I'm not sure what that means. So can you elaborate? What do you mean?
I wonder whether we could just change the progress of the proof, and we require some way to have the post condition on B and some way to have the post condition of C.
Right, that's correct actually. So whatever you are doing to prove B here and prove this post condition C here, you can actually do it at the same time and just directly prove this. So I'm not going to give you a formal proof of that, but this is what's known as completeness. Basically, any Hoare triple that holds can actually be proven using one of these, using a combination of the rules that we already have. So our logic is complete. We don't need that. So the rule is correct, but we don't need it. Okay, one final thing is, what about non-determinism? So what if my program can have non-determinism in it? So it's a non-deterministic combination of P and Q. Then what kind of rule should I have for this? So what should I write above this line? Any ideas? So you can actually think about the definition of Hoare triple and based on that figure out what we should write in this rule. So what does P star Q mean? It means that we either run P or we run Q. Yes, that's correct. What's in the chat is correct. So previously we had a similar case with if, where we either ran the then part or we ran the else part. But in those cases, there was also a condition that we checked. The only difference here is that we are not really checking a condition. It's just that we either run P or we run Q. So we can have this. So if starting from a state that satisfies A and running P, I end up in a state that satisfies B. And also if whenever I start from a state that satisfies A and I run Q, I end up in a state that satisfies B, then of course this also holds because P star Q basically means either run P or run Q. Okay, so this is our rule for non-determinism. Yeah, and as I said at the beginning of this session, this is the last lecture about semantics. And we didn't really cover the semantics very deeply, and the reason is that I just wanted you to be familiar with the 3 different types of semantics so that we can use them later on in verification. And the main topic of the course, which starts from next session, is going to be about verification algorithms. So are there any questions?
To make this Hoare logic into an automatic tool, does the tool apply the proof rules in arbitrary orders, or it is actually automatic, or do we still need to specify something?
So when we say automatic tool, we have to basically differentiate between 2 cases. One case is verification, and that's basically a tool that gets a proof and automatically checks the proof, right? And the other case is synthesis, a tool that just gets the final Hoare triple and tries to find a proof for it. So these two problems are very different. And verification is much easier. So the thing about verification is that you can easily have a tool that gets a proof, so something like this. And even if it doesn't know which rules are which, it can just check if, for example, this deduction matches any of the rules that it has, or if this deduction matches any of the rules that it has. And in this case, it's actually not completely trivial because, well, right now what we are using as our pre and post conditions are very simple logical formulas. If you can have first order logic, for example, if you can have quantifiers in here, or if your programming language is more tricky, if your programming language, for example, has arrays or other data structures, then it might actually be hard for a verifier to figure out if you can get from here to here with an application of, for example, the consequence rule, because it has to somehow prove that this one is a consequence of that one, right? It's like the other way around. So it has to prove that x plus 1 greater than 0 is a consequence of n greater than 1 and x greater than or equal to n. So as long as your language for writing the preconditions and the post conditions is simple enough that the verifier can check these consequences, it can definitely check a given proof. But then the thing that is much harder is when you actually want to synthesize a proof. So if you want to have some sort of completely automated algorithm that just gets this final Hoare triple and tries to find a proof for it, that's going to be much harder. Because, well, first of all, it has to decide at each point which rule to apply. In some cases, for example, in case of if, the rule that it has to apply is unique. But in many cases, the rule is actually not unique. So one example is the consequence rules. You can basically strengthen and weaken in infinitely many ways. And the other important example is the while rule. So in the while rule, we basically have a very specific type of A, and this is called a loop invariant. And guessing the A is not so easy. So if someone gives the algorithm the correct A, then its life would be much easier. But otherwise, guessing it is not a trivial process at all. And again, at the end of this course, we're going to talk a little bit about invariant generation and invariant generation in special cases. So in summary, the answer is that this kind of system really helps with making things automatic. It definitely helps with automating verification. It also helps with automating synthesis, but there are a lot of other details too. And actually, there is a tool called Boogie, and I might show you an example of it maybe in the next session, which basically does this. So it gets the preconditions and post conditions and tries its best to find the proof. And it does a very decent job, but honestly, currently it only works on small programs and simple programs. So if you have a very complicated program, this probably wouldn't help. And the way things are done in industry right now is that you get semi-automated algorithms. So for example, again, in this Boogie, the idea is that the programmer gives hints to the automated framework. So you write a function or a program and you write its precondition and its post condition. And then you ask Boogie to, for example, prove that this Hoare triple holds. And if it succeeds, that's great. If it fails, then you can give it hints. You can basically give it invariants, or you can give it parts of the proof and then ask it to try to fill out the rest. So the state of the art is not completely automated these days. And there is also a good reason why it's not automated, and it will probably not be automated either, because, well, we have Rice's theorem, and almost all of the problems that you can specify with Horde triples are basically undecidable. So generally, if you give me a Horde triple and ask if this Horde triple holds or not, that's of course an undecidable problem. Why? Because we know that termination is undecidable. This is what Turing proved. And termination of P would be what? Can you write termination as a Horde triple? Well, we can write non-termination as a Horde triple, and that's also undecidable. We know that that's also undecidable, so we can do this. So if we ask this, this is equivalent to asking, is it the case that P never terminates? And by Rice's theorem, we know that this is undecidable. So there is no algorithm that can solve this for all programs P. Okay. Any other questions? Okay, in that case, we can just end the session. Thank you everyone for attending, and have a great Chinese New Year. Bye.